Hi, guys. All right, so we were just dealing with boiling, and we basically said that boiling is the temperature where the external pressure is equal to the vapor pressure that the substance produces. All right, and that's what this is what we were just going over. Right, so we can make substances boil, all right, at all sorts of different temperatures depending on what that external pressure is. Now, what if we're going the other way? Okay. Well, before that, so there are two ways to make a substance boil. One, raise the temperature of the liquid. Okay, that increases vapor pressure. Or two, reduce the external pressure. Now, what if we want to go the other way? What if we want to make a substance condense? Well, again, there are really two ways to make a gas condense. The first obvious way is if I said, hey, here's a gas, here's water vapor, how turn it to a liquid? You're just going to decrease temperature. If we decrease the temperature, we're going to decrease our kinetic energy. Our gas particles will move slower. When they start moving slower, the molecules will start attracting each other. And eventually they will condense. So that's one way that we can convert a gas to a liquid. Well, there's a second way that we can also do it, and that's by changing pressure. If we take a gas and we increase the pressure, generally our volume is going to decrease. In other words, we're forcing the particles closer together. Okay, so we're forcing those gas particles closer together. So the distance between gas molecules decreases. Now, what happens is we force those gas particles closer together. Well, eventually, those intermolecular forces start working. Okay, so as molecules get closer together, the intermolecular forces, the IMFs, kick in. The particles are attracted, and again, the gas condenses. So again, we can condense a gas in two different ways. We could just decrease the temperature, or we could just increase our pressure and force those molecules closer together until the intermolecular forces kick in and it condenses into a gas. Good. All right, well, there's some special temperatures and pressures that we need to talk about. We need to talk about the critical temperature. And that's T sub C. So let's define our critical temperature. For every substance, there is a temperature above which the liquid phase of a pure substance cannot exist no matter how much pressure is applied. So there's some point with every substance that would give it enough kinetic energy that no matter how much pressure there is, it will automatically be a gas. All right, there's just too much kinetic energy to be a liquid. Then there's something called critical pressure. In every substance, there is a minimum pressure that must be applied to liquefy that substance. So let's go back to our pot of water with this one. Oh, this is P sub C. Let's go back to our pot of water. Remember, this doesn't boil because there's an external pressure, right? So when my vapor pressure equals the external pressure, it will boil. So if this pressure is greater than my vapor pressure, we'll have a liquid. Well, what if there is no external pressure? That means my vapor pressure is always greater than my external pressure, and this will be a gas. Okay, it'll automatically be a gas. So if there is no external pressure, okay, you can't have a liquid because it's just going to automatically boil off. Okay, so every substance has to have some minimum pressure, right, to keep that substance as a liquid. All right, let's just kind of quickly summarize some things about phase changes. First of all, each phase change is a dynamic equilibrium. So let's say that we have liquid going to solid, or solid going to liquid. This is going in both directions. Okay, so this is melting and freezing. Okay, so if we were looking at our heating cooling curve, we're in this section of the curve right here. Now remember, temperature does change here. All right, we have both phases in here. We have both liquid and a solid. If we increase temperature, so let's say that we're right here. If we increase temperature, okay, it's going to melt more and it's going to go this way. If we decrease or we take heat away, it's going to go this way. Right? So we have this dynamic equilibrium. Right? So when we have this dynamic equilibrium, in this case, our freezing rate equals our melting rate. If we add heat to this, it shifts the equilibrium and melting rate is faster. And vice versa. If we take heat away, it shifts that equilibrium and the freezing rate increases. So we would have it freezing. We can say the same thing between liquid and gas. It's also in a dynamic equilibrium. Right? So we have both vaporization and condensation occurring. So our condensation rate here would be equal to our vaporization rate. Again, if we add heat, it'll shift the equilibrium. Vaporization rate will increase and it'll vaporize. If we remove heat, it'll shift the equilibrium, but it will condense. Let's see here. So let's look at a heating cooling curve. Okay, so this would be solid and liquid and gas. So this is where we're freezing and melting. This is where this is liquid, sorry. This is where we're condensing and vaporizing. Now, remember our equations. Okay, so we have Q equals MHF and Q equals MHV. So HF, okay, is our molar heat. This is called the molar heat. Okay, sometimes it's called the enthalpy of fusion. And this is the amount of heat needed to melt 1 mole of a solid. HV is the molar heat of fusion, molar heat of vaporization. Which is the amount of heat needed to vaporize 1 mole of a liquid. Now, in general, okay, these generally look like this, these heat and cooling curves. In general, the heat of fusion is less than the heat of vaporization. It's much easier to freeze and melt a substance usually than it is to condense or vaporize it. Okay? So why is this? Okay, in general, why is the heat of fusion less than the heat of vaporization? Well, when we're vaporizing, we have to completely overcome, all the intermolecular forces. And that takes a lot of energy. Okay. When we're melting or freezing, we don't have to overcome all those forces. We just have to give the particles enough kinetic energy so they can start to spin. All right, so that's why heat of fusion is usually less than heat of vaporization. All right. So the last thing we're going to talk about are what are called phase diagrams. So a phase diagram is a graph depicting the conditions of pressure and temperature where solid, liquid, and gas phases exist or coexist. So let me give you one that they all kind of look the same. So they're going to kind of look like this. It's a graph, right? And this will be pressure, okay? And this will be temperature. And they kind of look something like this. Okay, it's going to come up to this something like there. And you have point. And then this might do something like that. And then this will do something maybe like that. In this area where we have low temperatures and higher pressures, okay, low temperatures and higher pressures, this would be where we have a solid. At higher pressures and higher temperatures, down here, this is where it's a vapor or a gas. Okay? And in this area, we have a liquid. Okay, so this is what they kind of look like. Okay, and they can take different shapes. All right, but in general, you're going to have a line here. You're going to have a line coming up here like this. It could be shallower like this, and then this could be more steep. Right, but you're going to have something like this. Now, each region represents a pure phase. So up here we have only solid, and here we only have liquid, here we have vapor. The lines represent an equilibrium state between two phases. So both phases coexist. You have both of them, which is phase change, right? So let's look at a couple different points. Right? So I want to look at a point here, a point here, and a point here. And let's label this 1, let's label this 2, and let's label this one 3. So let's look at point 1. So in point 1, this is the line between a solid and a vapor. So if we're on this line right here, that means we have both solid and gas. So if I go across the line here, we're turning from a solid into a gas. Okay. So this is the equilibrium between solid and vapor or gas. Okay. Well, this is the equilibrium between sublimation and deposition. Remember, sublimation is phase change directly from a solid to a gas. Deposition is directly from a vapor to a solid. All right, let's look at 2. Well, this is where we have an equilibrium between a solid and a liquid. Okay. We would have, at this point, both a solid and a liquid. All right, so this is where our phase change is melting and freezing. Our third point is when we have liquid and vapor, liquid and gas. So this is our equilibrium of condensation and vaporization. Now, we got a couple other important points here. This is one of them right here, and this is, let's label that one number 4. And at this point, at point number 4, this is called the triple point. This is the point at which all 3 curves meet. At the triple point, all 3 phases coexist. Okay, so if we're right here, okay, this is going to be in a triple equilibrium. We'll have both solid, liquid, and vapor all happening at the same time at this very specific temperature and pressure. Right? For example, H2O's triple point is at 0.01 degrees C and 0.006 atmospheres. If we put water at 0.01 degrees Celsius and 0.006 atmospheres, we would have all 3 phases of water all at the same time, because that's what its triple point would be. Now, there's one other thing that I want to talk about, and that's right up here at the top end of this line right here. Okay, and it's this section of the graph right up in here. Okay, this point right here is called the critical point. And above the critical point in this area, we have what's called a supercritical fluid. Okay, so once we get above this critical point, okay, it's no longer a vapor, it's no longer a liquid, okay, and that substance is indistinguishable between them. And we start to get into something that we're not going to deal with, but we get into this supercritical supercritical fluid. So at our critical point, the liquid and gas phases are indistinguishable from each other. Okay, so above this temperature or above this pressure, we get what's called a supercritical fluid. Okay, and that's all you really need to know about that. So just for fun, let's look at and I'm going to try to draw the graph of CO2. All right, so it kind of looks like this. So it does this big curve, something like that, to that critical point. And then there's my triple point, and it does something like this. Okay, this is where we have solid. This is where we have liquid. And this is where we have vapor. And I want to put pressure in here. It's right about here. This is 1 atmosphere. So there's a couple things that I want to notice. So CO2, carbon dioxide, right? Most of the time it's a vapor. Okay. Most of the time it's a vapor. It can be a solid, right? But this little section here tells me that it can be a liquid too, but it's kind of hard to make it a liquid. There's not much, it's got to be under pretty specific conditions to make it a liquid. All right. Triple point. For CO2 is 5.2 atmospheres and negative 57 degrees C. So if we take dry ice, which is just carbon dioxide solid, okay, and we put it on the counter, what does it do? Well, it will sublime. It converts from a solid directly to a gas. Where is that happening on our graph? Well, it's happening right here, right? So here's 1 atmosphere. This is where it's normally happening. Okay, this is normally 1 atmosphere. All right, so if we have a solid, right, it's going to sublime right here. It's going to go right here at 1 atmosphere of pressure. Okay. So that's why dry ice sublimes from a solid to a gas, okay, at room temperature. Okay. Anyways, you're going to be asked to just read the graph, and you might have to know what the triple point is and what this point is, and you might have to tell me what's happening if we go from here to here or vice versa, okay, and do some things with this graph. Okay. All right, so that's where we're stopping for today. Hope you have a good afternoon, and we will see you soon.